On a routine flight over Indonesia in 1982, a Boeing 747 did something no airliner should ever do. All four engines failed at once. The culprit wasn't weather or mechanical failure. It was volcanic ash, invisible to radar, and hot enough inside the engine to melt into glass. This is Wings and Wrecks. How machines fail, and what saves the people inside them. The key lies in a temperature gap. Volcanic ash melts at about 1,100 degrees Celsius, but a modern jet engine burns at roughly 1,400 degrees. So the ash doesn't just erode the blades, it liquefies, turning to molten glass that coats the turbine and chokes the engine from within. How could a cloud that doesn't exist on any screen bring down all four engines? On June 24, 1982, a British Airways 747 climbs out of Kuala Lumpur into the darkness over the Indian Ocean. Somewhere ahead, Mount Galunggung is erupting, but the crew sees nothing. Their weather radar shows clear skies. And then, it happens. The cockpit fills with a strange white glow. St. Elmo's fire, dancing across the windscreen. One by one, the engines surge, then flame out. The captain's words crackle over the radio. "Mayday, mayday, mayday!" All four engines have stopped. The 747 becomes a glider, descending silently through the night. The crew works frantically, trying restart after restart. Finally, as the plane drops below 13,000 feet, one engine catches, then the others. But the mystery remains. What kind of cloud could do this? The answer lies in the ash itself. So why does a cloud of rock dust bring down a modern jet engine? The answer hides in a gap between two temperatures. Volcanic ash is made of glassy silicate particles. And glass, it turns out, has a weakness. Ash softens into liquid glass at just 500 to 800 degrees Celsius. But a jet engine's core runs at roughly 1,400 degrees. That's hotter than the melting point of the rock itself, so the ash doesn't just scrape by, it liquefies. So when ash is sucked into the core, it turns to molten glass that sticks to the turbine blades and nozzles, clogging cooling passages and choking the engine's breath. It doesn't just erode, it transforms. What happens inside the engine when that molten glass begins to coat the blades? The sequence of failure is brutal. First, the ash softens and sticks to the turbine nozzles, clogging the passages that cool the blades. Then, as the glass hardens, it chokes the engine's airflow, starving it of the oxygen it needs to burn. The American Society of Mechanical Engineers lists the damage in stark terms. The major forms of engine damage caused by volcanic ash are 1. Deposition of ash on turbine nozzles and blades due to glassification. 2. Erosion of compressor blades. 2 mechanisms, 1 engine, and both are fatal. But before the glass can clog the turbine, the ash has already been at work. As the particles race through the compressor, they act like sandpaper, eroding the blades that spin at thousands of revolutions per minute. The erosion blunts the blades, reducing their ability to compress air, and the engine loses power. And here's the catch. The erosion and the glassification compound each other. The eroded compressor delivers less air, the turbine runs hotter, and the molten ash sticks even faster. Within minutes, the engine starves and surges, and the flame gutters out. That is how a cloud of rock dust becomes a death sentence for a jet engine. So why did nobody stop it? The answer lies in a cruel irony. Volcanic ash is invisible to the very instruments designed to keep aircraft safe. Weather radar, the pilot's eye in the sky, passes straight through the ash plume as if it weren't there. The crew of Flight 9 saw nothing but clear skies on their screens, while the mountain ahead was tearing itself apart. But the cloud leaves clues. At night, the first sign is a strange, ghostly glow. St. Elmo's fire, dancing across the windscreen as charged ash particles strike the aircraft. Then comes the smell of sulfur, a sharp, acrid odor seeping into the cabin. These are the only warnings a crew gets, and they come late. For the crew of Flight 9, these clues came too late. The St. Elmo's fire was beautiful, even mesmerizing, but it was the last warning before the engines began to surge and die. By the time they understood what was happening, the damage was already done. The ash had entered the engines, and the glass was already forming. And that's the trap. Ash doesn't announce itself like a thunderstorm. It has no radar signature, no dramatic clouds, just a faint haze that can be mistaken for ordinary weather. So how does anyone see it? The answer would take years and a $150 million lesson to emerge. But the cost of that lesson was staggering. In 1989, a Boeing 747 flew into ash from Alaska's Redoubt volcano. The damage to its engines alone reached $150 million. A single encounter, one invisible cloud, and a bill that could have grounded an airline. That price tag makes sense when you see what ash does inside an engine. The major forms of damage: deposition of molten glass on turbine nozzles and blades, and erosion of compressor blades. Both mechanisms rob the engine of efficiency and surge margin until it can no longer keep running. And this is why the threat is so costly. Ash doesn't just wear an engine down over time. It can shut down every engine, all at once. The 1982 and 1989 incidents prove that a single encounter can cripple a modern airliner and cost airlines millions in repairs. So how does anyone see a cloud that radar ignores? The answer begins far above the aircraft, in orbit. Satellites watch for the telltale signature of ash, the way it reflects heat and light differently from ordinary weather. But a satellite sees a region, not a single flight path. Pilots needed something closer, something that could look ahead from the cockpit itself. That closer look came in the form of a sensor called a VOID, the Airborne Volcanic Object Identifier and Detector. Mounted on the aircraft, it fires infrared beams into the sky ahead, reading the unique thermal signature of ash particles. In trials, it has detected ash plumes from more than 30 kilometers away, giving crews the minutes they need to turn aside. And there is one more tool, silent and precise: LIDAR, which fires laser pulses and measures the light that bounces back from ash particles. It can map a plume's shape and density in real time. Together, these instruments turn an invisible killer into a visible hazard, giving pilots the one thing they never had in 1982: a clear view of what lies ahead. So the engine that once ate glass now refuses the meal. Modern airliners carry satellite feeds and LIDAR, and new sensors like Avoid see ash ahead, giving pilots the warning that Flight 9 never had. The cloud that shut down every engine is now a hazard to be routed around, not a mystery to be survived. But wait, if ash is just rock dust, why is it worse than ordinary sand? Sand erodes too, yet planes fly through dust storms. The difference is melting point. Sand silica melts far above engine temperatures, so it only scratches. Ash's glassy particles melt far below, so they don't just scratch, they transform. So what exactly is volcanic ash made of? It's a mix of pulverized rock, minerals, and volcanic glass, all shattered by the explosion. The glassy fragments are the key. They're rich in silica and aluminum, and they soften at surprisingly low temperatures. That's why they turn to liquid in the engine's heat. But back to Flight 9. After the engines died, the crew had to restart them in the dark. They descended to 13,000 feet, where the air was denser and warmer. The captain later said the engines restarted because the ash had cooled and solidified, breaking away from the blades. It was a lucky break, and a clue. And that clue led to a deeper understanding of the cost. The Redoubt incident in 1989 wasn't just a close call, it was a financial disaster. The $150 million repair bill included replacing 4 engines and the aircraft's skin, which had been sandblasted by ash. It was a reminder that ash doesn't just stop engines, it corrodes the entire plane. And so the story closes where it began. A jet engine, spinning at full power, flying safely past a plume that would have destroyed it a generation ago. The glass that never reaches the turbine is the quiet triumph of 40 years of investigation. The invisible threat has been made visible, and the sky is safer for it. If you want to know why machines break and how crews fight back, subscribe. Next up, our next video.